So this is just a small addition to the previous video. So let me call it part 3. So in the previous video, what we had done is we studied this problem of determining the fault current, and then we have taken a system, and then we built the Z bus, and then we also verified that by building Y bus and inverting it, and then it was matching, and then suddenly we realized that Z bus is nothing but the the diagonal elements of the Z bus nothing but the Thevenin's equivalent impedances calculated at that particular bus. So using that information, we calculated the fault currents. But then the question still remains: what about these are the fault currents after the fault? Under those conditions, what would be the fault voltages at each bus? So that was not asked in the question. So let me just copy this, and I'll take it to a new page. So this will be officially our third part of the video. So I'll just change this to P3. Now also, so I'll just add the question here. Also find post fault bus voltages. So okay, if this question was asked, how would you solve it? So the fault currents, so you can actually give an attempt, but then I am writing the fault currents were already calculated. So you can just refer to the previous video in this playlist. So I'll just write down fault location, and as a result of the fault location, what is the fault current? So bus 3, bus 2, and bus 1. So fault current, so let me refer to my previous solution that I got. So at bus 3 it is minus J 5.81. So fault current is minus J 5.81 per unit. Similarly at bus 2, this one minus J 13.86 per unit, and bus 1 is minus 17.04. Okay. So these are the fault currents I already obtained, in the previous video. We're already calculated. So these are the solutions. Now, of course, this is three different cases. So for the first one, I considered fault here. Then for the second one, fault is here, and for the third one, fault is here. Three independent separate cases. Now I want to find out the voltages. So for voltages, what happens is, because the initial currents are zero, so whatever Thevenin's uh, currents calculated to Thevenin's equivalent were themselves the fault currents and the final currents. But the initial voltages are 1. Initial currents were 0, but initial voltages are 1 all the time. And using the Thevenin's impedance kind of model, we will get the delta V. So changes in the voltages. So you all know V is nothing but Z bus into I. So if this I is delta I, then I'll get delta V. And then this delta V I'll subtract from the original V, and then I'll be getting the correct answer. So Z bus also we had calculated. So let me copy the Z bus also, which we had calculated. So I'll take this one. that is bus impedance matrix we already calculated. Now this part I'll just delete. Now what is delta I? So consider fault at bus 3. So when there is a fault at bus 3, the fault currents will be like this, delta I, or fault voltages. First I'll write fault currents. So 0, 0, and here it was minus J 5.81 per unit. So if I just refer to this, so the current being extracted out of the bus 3 is minus J 5.81. So therefore current being injected into bus, I think it should be negative of that. So it will be minus. So this is bus 3 and I have a fault, and the current going into the fault is minus J 5.81. That means current being injected into bus 3 will be J 5.81. So that is delta I. But anyway, you don't worry about this sign because we can always correct it later, because we know the voltages will reduce. So now what is delta V? Change in voltages. So nothing but Z bus multiplied by this 0, 0, J 5.81. Now there is already J in the Z bus and there is a J here. So J into J will be minus 1, and then this will be just multiplication. So what I'll do is I'll just simply ignore. So there is a J for Z bus and J here. So J into J will be minus, and then Z bus, and then it will be 0, 0, 5.81. So like this. So I go back to my MATLAB interface, and then if I run this earlier code, and then if I type Z, so in this variable Z, the Z bus is stored already. So if I just multiply this as a matrix multiplication, 0, 0, 5.81. So this will give me the voltages that are being changed. So delta V is nothing but, so here I can see 0.1859 or 0.186, I'll round off, and then 0.418, 0.418, and then 0.99942. So these are change in voltages. Of course, there's a minus outside, so that minus will be there. So now that means the voltage which, so what are the original voltages we pre-fault? So original voltage is assumed to be 1, 1, 1 everywhere. So now the change in voltages. So therefore, post-fault voltages, V post-fault is equal to 1 minus all this. So now I can write 1, 1, 1. So 3 ones as a column matrix. From this I will subtract my earlier answer. So I'm getting something like this. So this is 0.814, 0.814 per unit, and then 0.586 per unit, and finally this one is almost this is to the 10 to the power of 4, so it's almost 0. So that is what happened, because there is a fault happened, voltage fault happened at bus 3. The bus 3 voltage almost died, whereas the bus 1 voltage went reduced only up to 81%, and the bus 2 voltage reduced only up to 58 point, only to 58%. Earlier it used to be 1 per unit, it became this one, and this 1 per unit became this one. So this is how we calculate the reduction in the voltages or post fault voltages. Now let's quickly take up post fault voltages for fault at bus 2. So delta V is Z bus into delta I, right? So these are all matrices. So delta I is nothing but 0, and what was the fault current at bus 2? 13.86. So I'll just keep 13.86 here. I'm not worried about the magnitude and all. There will be overall one minus will come. So let's go back. and here 13.86, and finally this current will be 0 because it's a different case. So now you see I'm getting something like this. So delta V equal to 0.443, 0.998, or almost 998. This is in per unit. So there will be a minus sign also, the one which is outside. So now therefore the final voltage is nothing but 111 and then minus of this one, or plus minus 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 443,998. So this is approximately equal to 0, these two, because 0.998 is almost equal to 0, and this one will be 1 minus 0.443, so maybe it is 755, is it that? Yeah, so 557. So for the fault, earlier the voltage went from 1 per unit to 0.81 per unit, and whereas here you see the bus 1 voltage is reducing even further because fault has moved close to the generator. And you notice that the bus 3 and bus 2 both are 0 volts because fault is at bus 2, and bus 3 there is no load, so both are at 0 volts. So finally fault at bus 1. So when the fault is at bus 1, so what is my delta V? So there's nothing but Z into, what is the fault current? At bus 1 it is 17.04. So I'll say here 17.0400, the minus sign. $17.04. Now if I run this, so I'm getting like this. So 0.999, 0.545, 0.545. This is all in per unit with a minus sign, of course. So this is change in voltage. So therefore, what is the actual voltage? So 111 plus this one minus 0.999 minus 0.545 minus 0.545. So here you'll get 0 volts at the faulted bus, and then 1 minus 545. That will be 0.455 and 0.455. So these are post-fault voltages. Now you see, wait a minute, if the generator itself is 0 volts, how come there is a 45% of voltage at bus 2 and bus 3? So just you recollect, there is a generator at bus 2 also. So this generator is generating some voltage which is provided for bus 2. But even that voltage has reduced. So I hope now you understood how to calculate the post-fault voltages. So this will be, I thought I'll not make this, this topic I kind of dropped before. So then suddenly I realized this is also an important topic to know post-fault voltages. So that's why I had kept it. So what is, if the voltage at this was 11 kV, now the base voltage was 11 kV, it will be almost less than half of 11 kV. So you cannot operate at that low voltage, the generator. Even the generator has to be tripped. So of course the closest to the fault, if I trip this generator 1, then generator 2 will bounce back to its original voltage and it starts generating. So anyway, so this is a video about calculating the post-fault voltages.